Okay. So today we will do, or today we will learn about the analysis of portal frames using flexibility method. Okay, all of you, please pay attention because this is the last part. This portal analysis of portal frames is the last part of your third unit. Okay, so today we will consider a problem. So I hope please all of you write down this one. Okay, so the question is analyze the frame using flexibility method. EI, it is given as EI equals to constant. Okay, now what does or how does the frame look like? So the frame looks like this. This support is fixed. This support is is hinged. This is A, this is B, this is C, this is D. Okay. Now this length is 10 meters. This length is 6 meters. We have a UDL over here, and the UDL is 2 ton per meter, and I have a point load at this joint B, and it is of magnitude 8 tons. Okay, and the moment of inertia, this is I, this is 2I, and this is I again. Okay, so this problem we have to solve using the flexibility method. So what we need to do, please pay attention. So the first step is step 1. That is, what is the degree of static indeterminacy? So degree of static indeterminacy. Okay, now what is the degree of static indeterminacy? So here, as you already know this one, that I'm putting it in highlight. Okay, so here we have one vertical reaction, one horizontal reaction, one moment will be there, and here we have another vertical reaction and one horizontal reaction. Okay, so total we have 5 unknown reactions. And how many equations are there? Equilibrium equations, we have got 3 equilibrium equations. So I can write that SI, static indeterminacy, equals to R minus R. So R is, we have 5 minus this small r is the number of equilibrium equations, that is 3. So we have got 2. The degree of static indeterminacy is 2. It means that within these 5 reactions, what we have to do, we have to take any 2 as redundants or extra. Okay, so let us take this one and this one as the extra reactions. Okay, so let us write regarding that one. So since the degree of, you can write, since the degree of static indeterminacy of the structure is 2, let us select the horizontal and the vertical reactions at joint D as redundants. Okay, let us say this is figure 1. For example, let's say this is figure 1. Okay, so let's say this is HD, this we call it HD, and this we call it ED. Okay, so therefore the release structure the released structure is this one. So what we are doing, this is the released structure. So I am removing that joint. Okay, and it will be like this. The structure will be like this. So this one is 2 ton per meter. This is, here we have again, it is 8 tons. This is A. All of you please mute your mics. This is C. This is D.
इधर अब स्टार्ट है बिन
Okay, so this is 2 ton meter. This is A, B, C, D, and this one is 6 meters. And this is 10 meters. This is given as I, this is 2I, and this is I. Okay, so this is figure 2. Okay, so this one I'm putting something here. So this is, here it is coordinate 1 and here it is coordinate 2. Okay, so the next thing is, next step, that is step 2. Now what is the step 2? The step 2 is the analysis of the released structure. Okay, So how we are going to analyze this release structure? Okay, see, this one and these ones, this 1 and 2 are only the coordinates. Okay, your release structure will be this is your release structure. What we have to do, we have to apply or wait, let me explain, then I will remove this one. So what we need to do when we will analyze, when we will apply the unit load, so we will apply the unit load at joint D in this direction, and then I will apply the unit load in this direction. Okay, so for the timing I am removing these ones. Okay, so this becomes your released structure. So now we will, whatever we have learned in the previous class, the same concept we will apply here. Okay, so let us say, let m, let m equals to the bending moment at any point due to the applied loads. And small m1 equals to the bending moment due to the redundant or or let's say due to the unit load at coordinate 1. Okay, so please remember that this is your coordinate 1, this is your coordinate 1, and this is your coordinate 2. Okay, so similarly m2 equals to bending moment due to unit load at coordinate 2. Okay, and we all know this relation. So d minus dl d minus dl equals to f into p. Okay, now what will be the size of this one?
2. 2 into.
So this is 2 cross 1, this is 2 cross 1 again, this is 2 cross 2, this is 2 cross 1. Why? Because the degree of static indeterminacy for the structure is 2. Okay, so now in this current problem, this matrix will be 0 because in the question there is no settlement of supports or anything is given. Okay, so we only have to deal with this DL, this flexibility matrix, and the redundant force matrix. Okay, so now this DL, this already you know that it is D1, it consists of D1L, D2L. Okay, if three redundants will be there or the degree of static indeterminacy is 3, then D1L, D2L, D3L likewise. Okay, and again this D1L is integration of 0 to L m into m1 into dx by ei, and this d2l is integration 0 to L m into m2 into dx by ei. Okay, and this f equals to, this is of size 2 cross 1, this is of size 2 cross 2, so this is f11, f12, f21, f22. Okay, so this, so now where this f11 is equals to integration 0 to L m1 square dx by ei, f12 equals to f21 equals to integration 0 to L m1 m2 into dx by ei, and f22 equals to integration 0 to L m2 square dx by ei. Now you may ask, what is m1, m2 and capital M? So already those are explained here. Okay, so now in order to determine the small in order to determine these, now in order to determine this m1, or sorry, capital M, m1 and m2, we need to make a table. Okay, so let us make that table. So the first. So the first is section. Okay, so now I'm drawing the structure again here for your convenience. This is the current structure now. This is 2 tons, 2 ton per meter. Here we have got 8 ton. This is A, this is B, this is C, this is D. This length is 6 meters and this length is 10 meters. Okay, so this is I, this is 2I, and this is also I. Okay, so this is not 0, this is D. This is D. Okay, so let us start from the joint where we have taken the redundance. So let us start with the D. Okay, so the first member is, or the first section is DC. Then the next section is CB. Then the next section is BA. Okay, so these are the sections. Now the next one is the limits. So limits means from what length to what length it is there. Okay, so it is from here to here, it is 6. So 0 to 6. Sorry. Not limits. We will first start with the origin. We will go sequentially. Origin. Okay, so for this segment CD, let us take D as the origin. Okay, so D, then for CB it is C, for BA it is, let's say the origin is E, means from here we will start the value of X. Okay, now the next one is limits. So as I said, from this is from 0 to 6, 0 to 6. This is 0 to 10, 0 to 10. This is 0 to 6 again. Okay. Next one is EI. So EI value is here it is 1, here it is 2, and here it is 1. 2, 1, 1. Okay. Next one is M. Next one is small m1, and the next one is small m2. Okay, so I'm again drawing this the same, or I will do zoom in. Yes, zoom out. So now this m value we are supposed to determine from here. So m, as I said, it is the moment at any section or any point due to the applied loads. Okay, so now let us say I'm considering this is segment DC. Okay, DC. Let us take, I'm considering X is from here. Okay, let's say I'm taking X as here. This is up to X. So this length is X. So within this, any externally, any moment at any section here, what is the moment at any section for this segment? Any loads are applied here? Yes or no? So since there are no loads applied in section CD, okay, so within this length, the moment will be 0. Okay, now let us take a section, next section. Let us take, I'm erasing this one. So let us take the section here for let us take the section as X. Okay. Let us take the section here starting from C. So what will be the moment due to the applied loads, externally applied loads? So this is only 2 ton is applied. Okay, so can I write 2 into, sorry, 2 into, so it is 2 into WL square by 2. Okay, L is here X, so W into X square divided by 2. So this 2 gets cancelled, so this becomes X square only. Okay, now similarly this one for BA. For BA, if I take a section here, if I take a section here, so for section BA, this force will act, and apart from that, this 2 ton per meter, this will also have certain contribution. So what will be that one? So can I write the moment here is 8 into X. This is for this one. So 8 into X plus this is 2 into 10 into 10 by 2. Okay, so this one becomes 8x plus 100, the moment at this section. Okay, 8x plus 100. Okay, now this part is over. So next one is, sorry, the M1. Now how we will find out M1? So as I told, M1 is the moment at any section due to the unit load applied at coordinate 1. So this is our coordinate 1. So in this coordinate 1, we are applying 1 kilonewton. And please remember that we are removing the all other externally applied loads. Okay, this is A, this is B, this is C. So we are not considering any other applied load. And again, this length is 10 meters and this length is 6 meters. Okay, so if I apply load here and if I consider a section here, then the moment due to this load in this section CD or DC, whatever you may call, this is, let's say, X. So this becomes 1 into X. Okay, done. Now, if I consider a section here, if I consider a section here for the section BC or for the segment BC, okay, then let us say this is X. So moment at this point due to this load will be how much? This is 6 meters, so 1 into 6 only. Okay, no X will be there because X is not varying like this. So see this one. So this is 6, 1 into 6 equals to 6. Okay. Next. Now let us take for section BA. Let us take the segment for BA. Let us take the segment here. Let's say this is X from along this line. Okay. So what will be the contribution for this force? What will be the moment contribution? The moment contribution will be again 1 into 6 and it is minus X. So it is 6 minus X. Okay, this one. Okay, so 1 into, sorry, this one is 1 into 6 minus X. Okay, now this M1 is over now. Now for M2, what we need to do? The M2 will be this one. This we already know it is as 10 meters. So at M2 we will apply unit load here at coordinate 2 in the direction of coordinate 2. Okay. So due to this, what is the value of moments? That we will find it out here. Okay, so let us take a section here. Okay, so if we take the section here, then what will be the contribution of moment due to this force? So this point, this force 1 kilonewton, it is passing through this point, so the moment contribution will be 0. Okay, now let us take a section here. So moment at this point will be, due to the externally applied load, will be 1 into x. Okay, so 1 into, or 1 into x, I'll let dot 1 dot x, 1 into x. Okay, now similarly here again, let us take the section at P. This is x. Okay, so it is 1 into x. Okay, sorry, this will be minus. This will be minus because this is generating an anti-clockwise moment. Okay, so this will be again, so this is 1 into x, so minus 1 into x, and here this will be 10 into minus 1 equals to minus 10. Okay, no x component here because x is along this direction and the force is at an eccentricity of 10 meters from the joint B. I am considering the, sorry, this is not A, this is B. Okay, so this is your table which gives you the value of capital M, small m1 and small m2. Okay, so next is we will determine in the next, we have to determine this one D1L, this D1L, D2L, F11, F12, F21 and F22. Okay, so let us write, or let us find out D1L. So D1L, we already know that it is integration 0 to L M, sorry, not M1, this is M into M1 into dx divided by EI. Okay, so M is this one. So for each section, for all the sections, we need to find out that value. Okay, so now, so this one equals to, so M1 is, so M is 0, M1 is x, so integration this DC is 6, integration 0 to 6 into 0 into x divided by EI into dx plus integration 0 to 10, this is 10, integration 0 to 10 is x square into this M1 is 6 divided by EI, and here it is EI is 2, so 2 EI into dx plus integration 0 to 6, and it is 8x plus 10, sorry, 8x plus 100 into 6 minus x into dx. Okay, so this becomes 0. So we are left with integration 0 to 10 6x square by 2ei into dx plus integration 0 to 6 8x plus 100 into 6 minus x into dx. So if you integrate, you can integrate using calculator. So if you integrate, you will find that, all of you please check the value. So you'll find this one as 3088 by ei. Next one. Okay, so since I will be using this, I'll be using this table. So what I will do, I will just slide it here and I will write here. Okay, so d12 equals to integration 0 to L m into m2 into dx by ei. So it is, so this is m, so this one into this one, it is 0, so it is integration, so I am not writing that one, so 0 into 0 is 0, so this is x square into 1 minus x, so integration 0 to 10 x square into minus x by ei, it is 2 ei into dx plus integration 0 to 6, it is 8x plus 100, 8x plus 100 into, this is minus 10, minus 10 into dx by ei. So this becomes integration 0 to 10 x cube minus x cube by 2ei into dx plus integration 0 to 6 8x plus 100 into minus 10 dx by ei. So if you integrate this one, you will get d12 equals to minus 8690 by ei. Okay, so I'm erasing this part now and I will calculate the f1 value. Okay, so f11, here we already know this, f11 equals to integration m1 square dx by ei. So that we will write here. So f11 equals to integration 0 to L m1 square dx divided by ei. So that becomes integration, the first one is m1 square is x square, so integration 0 to 6 into x square by dx, sorry, not dx by ei, then plus this is m1 square is integration 0 to 10, this is 36 into dx divided by ei, this is again 2. Okay, next one is this one. So plus integration 0 to 6, 6 minus x whole square by ei into dx. So if you integrate and find out, I'm writing the final answer as 324 by ei. So this implies f11 equals to 324 by ei. So the next one is f21. So I'm doing it here. Okay. So next is f21 and f12 and f21. So f12 equals to f21 equals to integration 0 to L m1 m2 into dx by ei. So it is, the first one is m1 into m2, this is m1 m2, this is 0. Okay, now this is 6 into x. Okay, so it is integration 0 to 10, 6 into x by 2ei into dx plus this is 6 integration 0 to 6, 6 minus x into minus 10 divided by ei into dx. Okay, so this becomes, so if you integrate that one, you will find that it is coming as minus 330 by ei minus 330 by ei. So the last one, that is f22. So f22 equals to integration, I have written already it here. So integration 0 to L m2 square dx by ei. So it is m2 square is, this is 0, this is x minus x into minus x, so it is plus x. So integration 0 to 10 x square divided by 2ei into dx plus this is integration 0 to 6 minus 10 into minus 10, 100 into dx by ei Okay, so if you integrate this one, then the final value will be 766.67 divided by EI. Okay, so now the next step is we'll finish this step 3. So step 3 is determination of the redundants of the redundants. So we already know this is D minus DL equals to F into P. So this D already we know there are no sinking of supports. So this implies this minus DL is minus 3088 divided by EI, and it is plus 8690 divided by EI equals, this is F matrix is 324 by EI minus 330 by EI, then minus 330 divided by EI, and this is 766.67 divided by EI. This is F matrix into the P matrix is, what is the P matrix? It is HD and VD. Okay, so if you solve this one, you will find HD and VD. So this will go that side, it will be inverse. So it is coming as 3.6 tons and 12.8 tons. If any correction is there, please let me know. I'll happy to correct the answers here. Okay, so these are the HD and VD. Okay,